Hello, today we're going to talk about preparing an interface for an SEL311L. We're going to also showcase a simulation with two of those devices connected to real-time simulator from Typhoon HIL. So we have these two SEL311Ls, they're connected to our HIL 604 and they're connected actually through the HIL Connect. So the signal level outputs of the HIL go through the HIL Connect. This device amplifies or readjusts the signals and feed them to the relay, so that the relay would understand that they're connected to the secondaries of PTs and CTs, but they're actually connected to real-time simulation. We can even argue that this could be a digital twin of a real system, and we're really fooling these relays. So I'll open my schematic editor. I already have one blank canvas open, and what I'm going to do is just place some components. So for example, to represent my grid, I can use a three-phase voltage source. Then I can get a transmission line and connect it to my voltage source, and with this effectively we represent our grid, so it's an equivalent representation. And here I can come and define how I want to parameterize this component. For example, I can put 100 kilometers, or I can put a variable here that defines that length. So I will, for example, call it length line 1, and I can define my resistance impedance matrix and my inductance impedance matrix. But I will actually also use some parameters here like this, and I can do the very same for my inductance. And then basically I can start building the interface for one of these relays. So the first thing I'll get is a contactor. Place it there. I can double click on my contactor, select it to be controlled by the model, because I'm going to map the inputs from the relays to this through the model. And I can even define the delays for this break to operate. I'm going to put 60 milliseconds here, for example. And now here, what I want to do now is to put a meter representing my CTs and PTs, and I put it in with the specific orientation because I want to measure the current flowing to the breaker. I would connect it like this, and then what I want to do now would be to actually map the digital inputs. So inputs to the simulation mean output from the relay, so I want to map those here. These will be closed. This will be open. And I'm going to use a set reset flip-flop like this. So close is set, open is reset, like that. And the only thing is that we have left in this stage would be to configure the channels that we're using as digital inputs, or where we connected the digital outputs from the relay. So this is going to be number 2, and this one I'm going to leave it as 1. So basically with this we have our interface for the relay, and we can keep on building our model. But I won't proceed much. I want to say that we can, for example, come here and create a subsystem from this selection, and with that we can simplify how it looks like, or we can readjust it. We can rename the whole subsystem, for example, as Bay 1, and I can even create a mask on top. Also, here on the transmission line, I said about putting some of these variables here, defining the parameters. So if we want to leave it like this, we can use here on top the initialization script to define those variables, such as length line 1 equals 100 kilometers, and then I can define my R line 1, and I can really just write my impedance matrix here. But since this component uses ABC impedance, it can get a little bit complicated. So what you could do is actually use some Python code to do that conversion for you. So for example, I could use this code that I already have, and you could create your own code. But this code specifically, what it does is to create this object, this class cable, and it has some properties or some attributes inside, and I can use impedance in the sequence frame or symmetrical frame to define this cable. So it might be easier for me to use this than to do a calculation somewhere else and parameterize my lines. So basically I could do something like cable 1, and then I just construct this object, oops, something like this. Now I'll have a cable with this impedance, and I could simply then pass it to my other objects, like resistance line is equal to cable 1, and then I call my ZABC matrix. Actually, that's not what I want. I want my RABC matrix. I can do the very same for my inductance. So something like this. And I really simplify it so that I don't need to worry about the matrices, the calculation. It's already done by this class, and I can kind of group everything or every variable that I have on this initialization script. The other option is to use the mask of the components, as I said. So you can come here and go to mask editor and create what you want. In my case, I already created those components, so what I'm going to do is open a library file that I created. So I divided it into two categories. One is the interface for the SEL311L, and the other is the transmission line. So when I go to the SEL311L, we see how it looks like, just a simple subsystem with no pictures, nothing. But if I double click on it, I have some new inputs that I can apply: execution rate for signal processing, the delays for my contactor, but also I can define here what is the starting channel for my inputs. I know that they are going to be in sequence. That's how they're connected here on the hardware setup. But I know that in this case it would have to start with 1, or I could change depending on how I have this SEL connected to my hardware. But let's look inside. So a very similar approach. So I have some comments explaining what these inputs are. I have my meter here for the CTs, PTs, the breaker, very similar, but now I have all of these 7 digital inputs. Some of them I'm just observing, and these 2 that we use to drive the breaker are there, and they are mapped through the mask. I also added a few extra things. So this is in my library now. I can load it and use it much easier or easily. And I also created this transmission line, which is basically a mask on top of the regular transmission line that we have in our models. So in here you don't need to worry about any of that conversion that I was doing on the initialization script, because actually that very same code is kind of embedded here behind this mask. So I don't need to worry about it. I just parameterize my line with 0 and positive sequence components. I can still define my length in kilometers and my grid frequency. So if we look inside this component, we see that it's basically a transmission line. But you can also see that I added this enable fault checkbox. When I click on it, we get new parameters that we can set. So for example, fault position and the fault impedance. So now, since I check this box, if I press OK and look inside my subsystem, we see that a new transmission line was added, and also the dynamic grid fault. This component actually uses 4 switches to combine them and cause all types of short circuits that we'd like: phase to phase to neutral, single phase to neutral or to ground. So we can do everything here, and notice that it's much easier to parameterize. If I uncheck and press OK, of course, then I remove that fault and extra transmission line. So I think it was, I didn't say, but this position here, what it does basically is to divide the length of the previous transmission line into these new 2 transmission lines. So we divide them based on that parameter. So if we put 50%, that means that the transmission line section 1 here has the same length of the transmission line section 2. So by playing with that parameter, we basically, without changing anything on our schematic, we readjust the fault position. So basically, if I want to use this, if I wanted to continue my model here, the only thing I would need to do is to come here and actually load that library. So first thing, I should modify my library path. So I just find where I saved that library. It's actually in this folder already, and then I apply it temporarily. And then I can just simply reload my libraries. It takes a little bit, but once it processes, now we can see here that I have this folder called mylib. That's the name that I gave to my library, and then I have those 2 components that we've been looking into available here. So I can now start dragging and drop these ones. So for example, let's say that this is my second transmission line bay, my second relay bay. I want my another transmission line here so that I could cause a fault in a protected zone, you know, and I basically can keep on going and draw my whole circuit. That's not the goal right now. So what I'm going to do is open a new model that I have saved before. This model is right here. Yep. Notice that I have those very same components from my library. They are already here, and I wrote some comments to basically help us understand what we have here. So each of those SEL311Ls that we saw in the picture is connected to each of those or each of these bays here. We are only causing fault internal in this case. We could readjust the system for another case, and we see the reach, the protection reach of each of these zones and how they're parameterized in terms of impedance. So okay, the system is implemented. It's not that difficult anymore, since I already created my components, my library. The only thing I need to do is to compile. So I can click on this button. If everything is okay under the resources available, then it will pass compilation and it will load this model to our hardware device. And in here we can create our Scada interface, which is basically this interface, like very customizable interface for our simulation, where we can observe what's going on and also interact with the simulation. So for example, I could add a capture scope so that I can observe any signal that I'd like to, like voltages, currents. I just select here and I will be able to see them, also to capture those signals and save that. But I could also use some other widgets like digital display to read some RMS values, for example, such as here Bay1 RMS 0, or I can use Python for a little bit more complex or complete approach to these widgets. Again, I'm not going to waste time in this demo doing that, but I'm going to open one Scada interface that I prepared. So there are two macro widgets here, down here. They are very important because one of them is setting the outputs. So I showed a little bit, or very quickly, how we were setting the digital inputs to the simulation, or digital outputs from the relay to command the breaker. But this is how we map the analog outputs of the HIL or to the analog inputs of the relays. So basically these are the outputs of CTs and PTs, and we're just selecting to each channel we're going to set those variables to, and some scaling so that we are within the range, signal range of the outputs of this HIL 604 device. We're also mapping this digital output, which is the feedback on the state of our breaker, so that the relays understand how the breaker is operating. And on the other macro widget, I'm just collecting some data on a cycle at every 250 milliseconds, and I decided to do this just to simplify a little bit my other groups. So the data captured there is sent to these other widgets, and I can plot informations of voltages and currents and everything. So enough of that. I think we can start the simulation, and I explain the rest as we go. So notice that our system is set to 33 kV. Right now we're measuring here in line to neutral the voltages. We're calculating the impedance seen by the relays in the sequence frame. Notice also that these LEDs are showing that the breakers are open, so we should give pass command to the SELs so that they can close these breakers if there's no fault. That's where these two widgets, or two group widgets, come handy, because we're using serial communication, and we're using Python with some functions that we implemented also here on the initialization script. So for example, this first function would open the serial port through the COM port specified, and then we can close it if needed, but we can also parse the response and do something else, like change the access level, and also request the command breaker to, or request command to the breaker, so close or open the breaker. We can control some remote bits, reset the target of the relay, and also read some target rows from the relay to understand how it's operating. So I can come here and click connect. We can read on the bottom here that it connected to COM port number 2. I defined the COM port here on the group. So this means that I could, copy and paste this group and just define my COM port and baud rate here, and that would be very simple to connect these widgets to another relay. I can then give command to access level 2, and we can even read here that we made it, and then I finally pass the command to close this breaker. We can see here that the breaker closed. When we close this breaker, all these breakers, the current would still not flow. So I'm connecting to the other relay through COM port number 5. We can see on the bottom here that that's how that connection was established. I can then access level 2. Yeah, we're there, and then I can give command to close, and we can see here that the breaker closed. So we're ready to do any sort of test that we'd like. So what I'm going to do is to just set up here on my scope a capture, because I want to see what happens during a specific fault. So I'm observing voltages and currents, but I'm also observing the status of my breaker and the commands that I receive from the SELs. These are the commands to trip. So okay, I'm going to use one feedback of those contactors of the dynamic fault as a trigger source. So I come here, I select that. So this is on phase A, and when it's a rising edge, meaning that it's closing, that's when the fault is applied. That's the moment I want to capture this, and I will put a 15% offset in terms of time, so the event will happen a little bit early in my capture. So I can trigger here, set the trigger, it's waiting for the capture, and what I'll do now is I'll apply the fault. Let's apply the basic 3-phase short circuit. We can see already that the breaker is tripped. We also see that we were able to capture our data. So let me just organize it a little bit here by adding a cursor here right at 0. We can add a cursor then at the end, or if we zoom in, we can really observe the moments. So this is the breaker feedback, which would be around 4.4 cycles of 50 Hertz. That's what we use here. This is one very quick example on how we could simulate a system and have these SELs interfaced with it. If we want to read a few things from the SELs right now, we can, for example, read a target row. So we see that it recognized fault on A, B, and C, and we can also read the information from the other relay, and we can see here that it actually observed the very same problem at the network. This is the first demo, and I'd like to proceed for the second one.